So let's solve this problem. Determine the force in each member of the truss and state if the members are in tension or compression. How many loads do you see in this problem? Loads put onto the truss. Two loads. So 900 and 600. Okay. How many places is it supported with the surroundings? It's supported in 2 places, at A and at C. Okay, describe the support at C. Well, how do you describe that at C? It's a pin-connected support at C. And how about at A? Is that a pin-connected support at A or a slightly different connection at A, a support at A? It's a roller support. And often you'll find out in bridges, and maybe you've walked around and you've hiked underneath bridges, you look up underneath, and you can see where the engineer has kind of pinned on one end and rockered or rollered, typically rockered on the other end, to handle thermal expansion contraction, because cold winter days contracts and they have expansion joints. It's a practical issue. So anyway, this is pretty common. So how many members are there that they asked us to calculate the force in each member? Well, how many are there? Well, there's a member that goes from here. That I like to try and order them. I know that they have F and A on the ends of this member. So you could call this member AF or member FA. To me, there's no distinction. I personally like to put the first letter to be the first letter in the alphabet. So I would like to talk about solving for the force in member A to F, not the force in member F to A. But again, there's no real distinction. It's just the force assumed to be in tension for the analysis for that member. So we have these members. I would make a list of all the members. Maybe I should have started that and just say we have member A to F, done. Member E to F, member A to E, member DE, member AD, member AB, member, oh boy, BD, member BC, member CD. Whew, that's why I wanted to start on analysis of trusses and method of joints, because it's going to take us a long time. How many unknowns are we asked to solve for? We're asked to solve for 1, 2, 3, 4, 5, 6, 7, 8, 9. And so the notation would be solve for the force in AF, and the force in EF, and the force in A to E, and the force D to E, and the force. And so those 2 letters would be subscripts on the force. Those are the unknowns that we're going to solve for. And if it's not too sloppy, I'm going to try and actually come up here as we solve for them and put them in here. But I'm afraid it's not going to look pretty after a while, because I'm going to have to go to clean pages to continue solving this problem. There's no way to solve the problem on one clean page. It's too much work. So a lot of unknowns. Now, where are our pins? There's a pin at each of these lettered joints. All right. Here's a strategy for solving the problem. First of all, I have some reactions at the supports. I have 2 supports. We talked about it. I'm going to say that at this support, there's a normal force at A. Because it's normal in the Y direction, I'd say AY. You could put N at A. That's another good label for it. And then I'd come over here and I'd say, well, I'm going to replace that pin connection by 2 reactions that are on this truss. Because of that pin connection, I'm going to say CX and CY. At this point, you could use some judgment and say, you know what? I think that if this, I think the CY is actually going to be a force holding the truss down. Good. On your free body diagram, you may want to put CY downward as the positive direction of the reaction CY. But because we're new, I would just recommend don't try and overanalyze it. You will get better at it. Just go ahead and put a typical direction. Now, you cannot put AY down. Why would that be wrong? Because the roller will let it lift off the surface. It will only stop it from pushing down into the surface. That's the only support it can provide. So it would go like this, AY positive upward. And you would anticipate a positive answer for AY. If you get a negative answer for AY, either there's a problem with your solution or there's a problem with the problem. The problem doesn't work. It's not in static equilibrium. All right. So I would recommend that you solve for these reactions at the supports first. Let's pause. All right, so in the interest of time, I'll pick it up here. A few of you have it, but you're going to do the equilibrium for the entire truss as a rigid structure, and you're going to do some of the moments, some of the forces, you know, X and Y, and maybe the moments around a particular point. And you should be able to determine that the reaction Cx, the support Cx is equal to 0, and that Cy is actually, as shown, negative 150 pounds. Is that negative sign important? Yeah, because I put it as positive upward on the truss, but actually this truss, what'll happen if that pin fails, then that pin would not be able to hold it down, because that's what really is happening. Cy is negative 150, and if it fails, it would rotate in the counterclockwise, pivoting around A. Cy is 150, and then AY is equal to 1650 pounds. Okay? So most of the weight of the truss and the load is supported by the reaction AY. But the way it is, this 900 pounds will kind of make it tilt around point A if Cy doesn't hold it down. Now, at this point, I think most students would be tempted to come in there with an eraser and start rubbing out Cy, because they just found out that it's not positive upward, it's actually down. And they would change Cy like that on their free body diagram. My recommendation, get one free body diagram, make sure you just assume the directions that you think they should be in, because we don't like to work with negative values, do we? It's error prone. But once you get it, you assume it, avoid or don't give in to the temptation to go back and erase it and change the free body diagram, because it just will have consequences. Maybe at this point it's easy enough, but definitely when you get into the solving with all these nodes, it'll be very error prone. So just stick with it. So what we're going to do is we're just going to leave Cy positive upward, and the answer for Cy is a negative 150 pounds. Yes? Now what we're going to do is we're going to run into developing. We're going to do method of joints. Means I come in here and I cut joint F free from everything else. I do a free body diagram of joint F. Okay, what does a free body diagram of joint F look like? And you're going to have a lot of these. You're going to do joint A. You're going to do joint E, joint D, joint B, and joint C. And so you're going to get a lot of, that's why it's not going to be able to keep it on one page. So joint F, what does the free body diagram look like? Well, don't forget the load. The load is 900 pounds, and it's consistent with the direction shown on my free body diagram. It's positive downward. And then we're going to assume that each of these forces are in tension. Those members are in tension. So we're going to have the force, because we cut right there, it'll be tension force in this member, E, F, and then this one is the force in A, F. So this one comes into play, and this one comes into play in the free body diagram for joint F. Sometimes, at this point, you can solve for some of these unknowns and start solving for them. I would add a piece of information that this slope is defined by a 3, 4, see the 3 and then the 4, 3, 4, 5 triangle. So I'd come over here and I'd add it maybe, 3, 4, 5 similar triangles, so I can easily pick off the components. And then I would do my equations of equilibrium, sum of the forces in the x, and I'm not going to write that all out because it's so much, but this is my equation for sum of the forces in the x must equal to 0. Basically, I'll have that the 100% of the tension force E to F plus, 4/5 of A to F is equal to 0. Does that equilibrium equation make sense? And then in the Y, we'll do the same thing. We have down 900 pounds. I could put a negative sign on it, but that's okay. And then I also have down pulling 3/5 of the force A to F equal to 0. So for each of the joints, I'm able to write only 2 equilibrium equations. They're both sum of the forces. Because it's a point, each joint is a point, I have no moment equation for that point. And so, at this point you look at it, sometimes you can solve for some of the unknowns. At this one you can, can't you? So can't we solve for A to F? Use your calculator. Tell me what you get for A to F, please. Then what I'm going to do is I should have cleaned this up a little more. I'm going to try and put it over here. I'm going to try and put our answers in this box over here. Because when you're solving these problems, it's easy to get lost. And you forget that you already solved for one of the parts of the solution that you're looking for. So we get, do we get 1,500 for A to F? So the force A to F is negative 1,500 pound. This was pound on that 900. Is that correct? Okay. Now, I recommend when you're solving these, especially for the exam, and they ask, give me your answer and express whether it's in tension or compression, that you give it a magnitude of the force. So over here, I would leave this as negative 1,500 down in the work area, but up here I'd put positive 1,500 pounds. And then the book uses either you describe it in tension or compression. And that's the notation used in the textbook. It's C in parentheses to say this member's in compression. Look through the textbook at how the problems are solved, the syntax, notation, etc., and follow it. And it'll be really easy then to understand your work. So now, don't go changing things. Just continue to leave that AF as negative 1,500 and use it in this second equation. And now you can solve for the force in E to F. What is the force in E to F? If A to F is negative 1,500 pounds. 1,200, okay. And is it a positive 1,200 pound? Isn't it? Okay, so we come up here and we're going to put similarly, hey, a positive 1,200. Both of our answers so far are positive magnitude, but we say it's actually what we assumed it to be. It's in tension. That member's in tension. So that's the way we're going to write all of our answers. We're going to say magnitude and then with the units and then either tension or compression. That's what the book does. That's what we want to get good at. All right. So that was for joint F. Okay. Let's jump over and do joint E. Joint E. So here is E right there. And we put a point here. And then we're going to have, they're going to have tension, 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 force, E to D, force, E, or A to E, and then the force, E to F, right? This looks a little bad, A to E. Okay, we'll do our equilibrium equations. Sum of the forces in the X. What does that give us? It gives us, well, that force E to F must equal to the force E to D. One pulls to the right, one pulls to the left. Okay, how about in the Y? The force A to E is the only thing acting in the Y. It's equal to 0. So the member E to A, or A to E, either one you call it, is a zero force member. They make a big deal of it in the textbook. And after you start knowing what zero force members are, you start looking for them, and then you can identify them. But probably at this point, just go ahead and solve for it, conclude that it's zero force, and then look at the equation, at the whole structure and say, why is that a zero force member? Because they got three coming together. If this is either in tension, it's just going to pull E down. Nothing's going to be able to lift it and hold it back up. Or if this member is in compression, it'll push the joint E up. And there's nothing to keep it at that location. Hence, the member A to E has to be. At first, just solve it. The math will show you that it's a zero force member. But after a while, you'll get good at identifying it. Do you see why it's a zero force member? Okay, so let's do this. Let's go ahead and put that right there. So zero force member. And then we already solved for E to F. So we can put in our magnitude for E to D. That's down here. Where is it? Or D to E. That's 1,200 pound in tension. All right. Now what I'm going to do is I'm going to pause. And what I'd like you to do is look at this truss problem and see if you find another. Don't call it out. Is there another zero force member? If there is, show me when I walk around. Which one is it? Once you get good at it. All right, so a lot of people were able to come over here and look, and they say, oh, the member from B to D has to be a zero force member as well. Again, you're thinking, okay, I'm going to do an equilibrium on joint B. When I look at the sum of the forces in the Y, there's only one member playing in the Y direction. And so the B to D is a zero force member. Professor, do I have to say it's in units of pounds and tension or compression? What do you think? 0, 0. I think I used that analogy before. If I'm dead broke, I may not have 0 pennies, $0, $0,000, 0 millions of dollars. It doesn't matter. 0 pounds, 0 yen, 0 whatever. You're broke, you're broke. So you can, at that point, say, units don't matter. Okay. Now we still have 1, 2, 3, 4 unknowns to go for. Let's do joint A. There's joint A. I'm going to draw it right here. And we don't forget our support, AY, from the surrounding. And we already solved for that. It's 1,650 pounds pushing upward. And then we're going to have, again, every member is assumed to be in tension, the force A to F. Now, whether or not you put this force A to E in there, or you just put force A to E is in there, but it's 0. I mean, if I was grading it and you already identified it as a zero force member, put it in the free body diagram, but you know that it's a 0 magnitude. But I don't think I would count off. There's no way. You know what you're doing, you'd get the right answer. A to D, and then we have the force A to B. At this point, I know this is a complicated joint, but I like to put little checks. I say, do I know this one, A to Y? Sure, it's 1,650 pounds. All right. How about the force A to F? Do I know that one? Because I'm looking for room. I come up here and I say, oh yeah, that's 1,500 pound force in compression. It's negative 1,500 pounds. Right? It's negative 1,500 pounds. And this one we put in there. So as I look at it, I have how many unknowns for the free body diagram for joint A? 2. Now I know 2 equations, 2 unknowns. I could probably solve for both of those. Let's do it. Let's solve what is my sum of the forces in the X look like for this problem. You would have F, A to F. If you want, I would go ahead and reintroduce that similar triangle, 3, 4, 5. And then over here we have a similar triangle, 4, 3, 5. Right? Okay, so the A to F, and then it's in the X direction is 4/5, and that's in the negative X direction, and everything else will be pulling in the positive X direction, which is 4/5 of the force A to D plus 100% of A to B. Let me pause. I wrote down an equilibrium equation for the sum of the forces in X for joint A. Is that correct? Thumbs up if you like it. I kind of put everything pulling on the left to the left and everything pulling to the right on the right. So I try to avoid minus signs, but hey. And then sum of the forces in the Y. I'm going to have AY pulling upward or pushing upward. Okay. I'm going to have 4 plus 4/5 of force A to F plus that 0 force member, so I'm going to leave it out. It has magnet, it's 100% of 0. And then we're going to have 3/5. Did I mess that up? I messed it up, didn't I? Isn't it 3/5 of the force A to F? 3/5 of the force A to D equal to 0. Does that look good? Go ahead and solve for them then. All right, so I ran out of time in class and didn't finish this problem, so let me go ahead and wrap this up in my office. So we'll scroll down here, and what we'll do is we'll take the X equation, and we'll go ahead and put in that it's 4/5 of the force in member A to F, which was negative 1,500 pounds, equal to 4/5 of the force in A to D plus the force in A to B. And then we also take the Y equation and we can re-express that. AY was a positive 1,650 pounds plus 3/5 of the force A to F, negative 1,500 pounds. Didn't leave enough room, move that over here, plus 3/5 force A to D equal to 0. So at that point you see we could solve for the force A to D from this equation right here, and it comes in at negative 1,250 pounds. And then going back, having a solve for force A to D, we could solve for force A to B. Force A to B comes in at negative 200 pounds. So what we do is we come up and put those answers into our table. So the force A to B will be 200 pounds, but instead of being in tension because it's negative, it's in compression. And then force A to D, the same thing, 1,250 pounds in compression. All right, at that point, what I need to do is get, again, a good visual on our diagram. We need to do another joint. We just finished analyzing joint A, although I don't have the label here, but this was joint A that we just finished analyzing. And we can come over and analyze B, or we can go over and analyze D. Let's go ahead and analyze joint D. And what I'm going to do is I'm going to scroll up here so we can kind of still see joint D. So here is joint D. So we cut right in here, and there's the joint D. We have our load of 600 pounds downward. We have the tension force in member D to E. We have a tension force in member A to D. That's bad looking. Tension force in member A to D, and a tension force in member C to D. And I'm going to leave out that 0 force member just to clean it up a little bit. And what we'll do is we'll put our similar triangles in. This is a 3, 4, 5 similar triangle, and likewise what we get is a 3, 4, 5 similar triangle. Okay, so with joint D, we take a look. What is our F, D to E? 1,200 pounds in tension, so that's 1,200 pounds. We can actually remind ourselves that we know that value. And A to D is, let me see, I should rewrite that a little cleaner. Force A to D is negative 1,250 pounds. So as we said down here, it was in compression. And so the only unknown is this force C to D. Well, we can go ahead and write our equation of equilibrium. Let's go ahead and write it in the y direction. So we'll have 600 pounds down due to the load. And then what we're going to pick up is also, we'll pick up 3/5 of the force A to D and 3/5 of the force C to D. Those are 2 down. And we have one unknown in that equation. Like I emphasized, this is known value. Force C to D then comes in at 250 pounds. So because it's positive, that's in tension. All right, so let's go ahead and add that over here. Force C to D is 250 pounds in tension. Okay, maybe I should have made that box a little larger. Bring it way over here. There. Okay, and then we have one more member, C to B. Well, we can do a method of joints on joint B. I think you can see what happens there. If you just have the tension force A to B and the tension force B to C, that the force B to C must equal A to B. And so that one's pretty straightforward. So that comes in at negative 200 pounds or 200 pounds in compression. So that's B to C. Well, with that, we wrap this problem up. It was a long problem. Thank you very much.